Hi everybody, this is Mr. Fowler again. This is part B. If you have not watched part A, please watch part A now. It's only 3 minutes long. And I will pick up with this where we left off before. So this is 2.1, yeah, or 2.2B. So we just learned how there were parts of the atom that bent towards the positive part, and bending towards the positive part meant that it was negatively charged. So Thompson's model was called the plum pudding model. Plum pudding. Okay. And it was missing protons, neutrons, nucleus, energy levels, and electron clouds. He had electrons, but he didn't put them in clouds. Okay. Next came Rutherfords experiment. So Rutherford added the nucleus and made the nuclear model. What happened was they shot a bajillion alpha particles at gold foil. Now, this doesn't do gold foil justice. If you hammer gold foil as small as you possibly can, it is so thin you can see through it. The Field Museum had a gold exhibit where they had a gold coin about the size of a quarter and showed how they hammered it out and basically wallpapered our chemistry room just with that gold coin. So if you have gold plating of something like that, like Notre Dame has a golden dome, that sheet of gold on top is really, 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 really thin, which is why it's possible to do because gold is really, really, really expensive. But so this is a super thin, super thin. And if you shot these big cannonball things at basically a super thin piece of transparent foil, you would expect most of them to shoot right through. And they did. So what happened was 99.99% of them shot through. But that 0.01% bounced off. Now normally, if you get a result like that, you go, oh, it doesn't really matter. But imagine if you are literally shooting a bazooka. This is me holding a bazooka at a wet tissue paper. Achoo! There, I made it wet. And I shot it, 50 bazooka shots through, and then one bounced off. Just go, oh, well, I just won't notice that one. You'd want to try and explain it because it is so surprising. So what they found out was that this piece of gold had a very small, very dense, very positive, because this was positive, nucleus. And the rest is mostly empty space. And the nucleus is about the size of a soccer ball on the 50-yard line in Soldier Field. So we're talking itty bitty 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 bitty. So this is a diagram of what Rutherford expected, and this is what he got. Okay, so he thought all these things would go through, and instead a couple of them bounced off, and he explained it by saying, hey, there's something in here that's very positive and very small. This doesn't do it justice. Really, it would be dink, that small. Rutherford's experiment. Learned. And we had this on there. There's a nucleus, is small, dense, meaning it's heavy for its size, and positively charged. It was still missing, they knew it was positively charged, but they didn't know what a proton was, didn't know what a neutron was. Whoops, that's not what a neutron. Didn't know what a neutron was, and he didn't know that electrons are in clouds. I don't know if that cloud's going to show up or not. I hope so. Bohr. Bohr used these things right here that are called spectral lines. So what he did was he shot energy at atoms, and when he shot energy at atoms, he shot white light at atoms, and notice, hey, a couple of these lines went away. Now, the whole thing wasn't absorbed, just these couple of lines. So what this said was an electron either jumped, it's like, pretend we live in a high-rise. You either live on the 15th floor or the 16th floor. You can't live on the 15.2 floor. That can't happen. So it had to make an entire jump up to another level. So the spectral lines showed that electrons make all or nothing jumps. Spectral lines gave us quantum, which is an all or nothing, leaps for electrons. All because of these things. Now these are kind of neat because this is also where we originally got the idea for a barcode. So because they had all these different things on there, all these different colors, and they said, oh look, you can have all these different things and a bajillion different ways to do it, so we can now put barcodes on things so that no one has to know the price of anything. You don't have to put stickers on them. You can just get a scanner that will read them and you can tell what's in it. That's how we know what the sun is made of, by the way. So an electron that's here can jump up, and once it jumps up to a level, it then eventually falls back down. So it would absorb, in this case, I know, is that pink light, and falls back down to get pink light. Bohr learned there are all or nothing energy levels. That's the jump. Quantum means all or nothing. So kind of like, what grade are you in? You're either a junior or a senior. You are not anything in between. Closer to the nucleus is lower energy than farther. So if you're close to the nucleus, you're low energy than farther away. Electrons emit energy when they're falling because they're forming a bond. So here's my nucleus, here's my electron, nucleus is positive. I'm forming a bond because positives love negatives and negatives love positives. Electrons absorb energy when jumping. So if I'm going to try and take it and rip it away, I have to break that bond. That's why it absorbs energy. The ground state is the lowest level, meaning the lowest energy. Excited state is higher than normal energy. And there's a larger spectrum of light than the visible light spectrum, so we can actually measure more things than that. Chadwick discovered the neutron. This was hard to discover because neutrons have no charge. That's all you need to know about Chadwick. This is the modern theory. It's called the quantum mechanical theory. Rings are wrong. Rings are wrong, rings are wrong, rings are wrong. Electrons exist in clouds, which we call orbitals, and we can predict where they probably are. So remember I kept saying electrons are in probability clouds? That's it. Then there's the Heisenberg uncertainty principle, which means momentum and position of a small particle cannot be known simultaneously to any degree of certainty. So this is weird. So if I go, oh, look right there. Danny is right there. Now if I know where Danny is, I don't know where he's going. I don't know how fast he's going or what direction he's going. Or if I figure out, oh, Danny's going northwest at 50 miles an hour. Yeah, but where is he? I don't know where he is. So it's weird. It's a mathematical oddity, but it is true. It's a proof, yay, proofs in geometry, that you can't know with any degree of certainty where something is and where it's going. So we call electron paths orbitals rather than orbits because they go in kind of these crazy ways. These are just shapes. You don't need to draw those, but just so you can see that they are not, look at that, that's not a circle, is it? No, it's a donut with a little doodad and a hoopy-doo on the bottom. So the basics again, you should know that protons are in the nucleus. They tell you the identity. Electrons are in clouds, not rings, outside of the nucleus, and they determine the chemical reactivity and charge. The neutron is in the nucleus, and it gives nuclear stability and mass. Review, you know the dudes. Dalton, Thompson, Rutherford, Bohr. Billiard ball model? That's him. Plum pudding model? That's him. Looks like a cookie. Planetary model is actually Bohr. And quantum mechanical model is Schrodinger. Schrodinger and Heisenberg. And you should know the experiments. Who did the cathode ray tube? That's Thomson. Who did spectral lines? That's Bohr. Who did gold foil? That's Rutherford. And that's all. Toodles.